Black holes are cool. There's something undeniably fascinating about an object so dense that not even light can escape it. We've all seen the swirling CGI animations, heard the dramatic music, watched stars getting shredded in simulations. But this isn't really about cosmic spectacle. This is about what happens when the universe breaks, when the rules that govern everything, matter, energy, space, time itself, get pushed so far that they fundamentally stop working the way you understand them. And the terrifying thing? Black holes aren't rare cosmic oddities. There's probably one lurking at the center of our galaxy right now. There are millions of them scattered throughout the universe. Some are closer than you think. So let's talk about what black holes actually are, how they form, what they do to everything around them, and what would happen if you got too close to one. Because understanding black holes means understanding the most extreme physics in the universe. It means confronting questions about reality that most of us would rather not think about. Are you ready? Here's what you need to understand first. A black hole isn't a hole. I know. The name is terrible. It's not an empty void, not a tunnel to somewhere else, not a cosmic vacuum cleaner sucking everything nearby into oblivion. A black hole is an object, a real physical thing. It's what's left when gravity wins so completely that nothing else matters anymore. Think about mass for a second. Everything that has mass creates gravity. You create gravity. Your phone creates gravity. The Earth creates gravity. The more mass something has, the stronger its gravitational pull. Simple enough, right? Now here's where it gets interesting. It's not just about how much mass something has. It's about how compressed that mass is, how tightly it's packed into space. Take the Sun. Massive object, right? About 1.4 million kilometers across, weighing in at roughly 2x 10⁻30 kilograms. That's a 2 followed by 30 zeros. The Sun's gravity is strong enough to hold 8 planets in orbit, along with countless asteroids, comets, and debris. But you could get relatively close to the Sun, well, as close as physics allows before you're vaporized, and still escape if you had enough speed. But what if you took all that mass, all 2x 10⁻30 kilograms of it, and compressed it down? Not a little. A lot. What if you squeezed the entire Sun down until it was only 3 kilometers across? That's when things break. At that density, at that level of compression, gravity becomes so intense that it warps space-time itself into a configuration that's wrong. The curvature becomes infinite at a single point. Space and time trade places. The normal rules stop applying. You've created an event horizon. The event horizon is the point of no return. Not metaphorically, literally. It's a boundary in space surrounding the black hole where escape velocity, the speed you'd need to break free from gravity, exceeds the speed of light. And since nothing can travel faster than light, nothing that crosses this boundary can ever come back. Not matter, not energy, not information, not light itself. Here's what's strange about it. The event horizon isn't a physical surface. You couldn't touch it. There's no wall there, no membrane, no force field. It's just a place where the geometry of space-time becomes so warped that all paths lead inward. Every direction you could possibly move points toward the center. Imagine you're standing on a hill. No matter which direction you walk, you're going downhill. There is no uphill. There is no level ground. Down is the only direction that exists. That's what space-time looks like at the event horizon, except it's not about space. It's about the future. Every possible future you could have leads deeper into the black hole. The size of the event horizon depends on mass. That sun mass black hole we talked about, its event horizon would be about 3 kilometers in radius. We call this the Schwarzschild radius, named after Karl Schwarzschild, who calculated this solution to Einstein's equations while serving in the German army during World War I. Dying of an autoimmune disease in the trenches, he was still doing physics that would reshape our understanding of the universe. For Earth, if you compressed our entire planet down, the event horizon would be about 9 millimeters across, smaller than a marble, A black hole with the mass of the supermassive monster at the center of our galaxy, Sagittarius A, has an event horizon about 24 million kilometers in diameter. That's roughly 60 times the distance from the Earth to the Moon. And here's something that messes with people. The strength of gravity right at the event horizon varies wildly depending on the black hole's mass. At the event horizon of a stellar mass black hole, say 10 times the mass of the Sun, the tidal forces would already be ripping you apart. We'll get to that. But at the event horizon of a supermassive black hole, millions or billions of times the mass of the Sun, you might not feel anything unusual at all. You'd cross it, not even realizing you just sealed your fate. So where do these things come from? Most black holes form when massive stars die. And I mean massive. We're talking stars at least 20 to 25 times the mass of our Sun. Maybe more, depending on the star's composition and how it evolves. Here's how stars work, in brief. They're fighting a constant battle. Gravity is trying to crush them inward. Nuclear fusion in their cores is pushing outward. For most of a star's life, these forces balance. The star is stable. Our Sun fuses hydrogen into helium in its core, releasing tremendous energy in the process. This energy creates pressure that counteracts gravity's crush. When the Sun runs out of hydrogen in about 5 billion years, it'll start fusing helium into carbon and oxygen. It'll swell into a red giant, eventually shedding its outer layers and leaving behind a white dwarf, a dense remnant about the size of Earth that will slowly cool over trillions of years. But massive stars? They go through this process faster and keep going. After helium, they fuse carbon, then neon, then oxygen, then silicon. Each stage produces less energy and lasts a shorter time. Silicon fusion, the final stage, lasts about 1 day. And then, iron. Iron is the end of the line. Fusing iron doesn't release energy. It absorbs energy. The moment a massive star's core turns to iron, there's nothing left to fight gravity. No more fusion. No more outward pressure. The core collapses. In less than a second, a core the size of Earth compresses down to maybe 20 kilometers across. The collapse is so violent, so fast, that it rebounds. The outer layers of the star come crashing inward, hit this incredibly dense core, and bounce. That bounce creates a shock wave that tears through the star. You're watching a supernova, one of the most energetic events in the universe. For a few weeks, this single dying star can outshine an entire galaxy of hundreds of billions of stars. But here's what matters for us. What's left behind? If the core's mass is above about 2.5 to 3 solar masses, the exact number is still debated, then not even neutron degeneracy pressure can stop the collapse. Neutrons are packed so tightly they're touching. Atoms don't exist anymore. It's just a ball of neutrons held up by quantum mechanical effects. And if there's too much mass, even that fails. The core keeps collapsing. Past the density of atomic nuclei. Past any density that has a name. It collapses until, well, we don't actually know what happens at the very center. Our physics breaks down there. But outside, an event horizon forms. A stellar mass black hole is born. At the center of every black hole is something called a singularity. This is where all the mass is located. Or at least that's what our current physics tells us. The problem is that our current physics also tells us it has no idea what's really going on there. According to general relativity, the singularity is a point of infinite density. All the mass of the black hole compressed down to literally zero volume. Infinite curvature of space-time. A place where the equations produce infinities, which in physics is usually a sign that your theory is incomplete. Does the singularity actually exist as a point of infinite density? Probably not. Most physicists suspect that quantum effects we don't yet understand become important at incredibly small scales. We'd need a theory of quantum gravity to describe what's really happening there, something that unifies general relativity and quantum mechanics. We don't have that theory yet. But here's what we do know. You can't see the singularity. It's hidden behind the event horizon. And that's probably a good thing, because if you could see it, if there were a naked singularity just sitting out in space, it might violate causality itself. The cosmic censorship hypothesis suggests that nature doesn't allow naked singularities to exist. Every singularity must be clothed by an event horizon. So far, we haven't found any counterexamples. Stellar mass black holes are one thing. Supermassive black holes are another beast entirely. These monsters sit at the centers of most large galaxies, including our own Milky Way. They're not just bigger, they're millions to billions of times the mass of the Sun. Sagittarius A(O), the supermassive black hole at the center of our galaxy, weighs in at about 4 million solar masses. The black hole at the center of the M87 galaxy, the one we actually got an image of in 2019, is about 6.5 billion solar masses. That's billion, with a B. How do these things form? We're not entirely sure. They're too massive to have formed from a single star. The leading theories involve several possible pathways. Maybe they formed from the collapse of enormous clouds of gas in the early universe, creating seed black holes that then grew over billions of years by consuming matter and merging with other black holes. Maybe they formed from clusters of stars that collapsed together in the dense cores of early galaxies. Maybe the first generation of stars, population 3 stars that formed when the universe was young and contained almost no heavy elements, were far more massive than any stars today. And when they died, they left behind bigger black holes to start with. Probably it's some combination of all these processes. What we do know is that supermassive black holes grow. They feed. Gas and dust and stars that wander too close get captured, forming what's called an accretion disk, a swirling disk of material that spirals inward, heating up to millions of degrees as it falls. This disk can emit more light than the entire galaxy surrounding it. We call these active galactic nuclei, or AGN, quasars. Some of the brightest objects in the universe. The black hole itself is dark, but the material falling into it. That's putting on one hell of a light show. Let's talk about what actually happens if you get close to a black hole. Let's use a stellar mass black hole for this, because the effects are more dramatic. 10 times the mass of the Sun. Event horizon about 30 kilometers across. You're in your spaceship, approaching. At first, everything seems normal. The black hole itself is invisible. There's no light coming from it. But you might see the distortion. Light from stars behind the black hole gets bent around it, creating a gravitational lens. You'd see multiple distorted images of the same stars, warped and stretched. You keep moving closer. If there's an accretion disk, you'd see it now. A ring of white-hot gas surrounding the darkness, glowing in X-rays and visible light. Beautiful and terrifying. At some distance out, maybe a few hundred kilometers, you start to notice something else. Time. See, time runs slower in stronger gravitational fields. This is real. This has been measured. GPS satellites have to account for this, or they'd give you the wrong location. But near a black hole, the effect is extreme. If you're watching a friend who's closer to the black hole than you, you'd see them moving in slow motion. Their clock would be ticking slower than yours. If they fell in and you watched from a safe distance, you'd see them slow down as they approach the event horizon. Slower and slower. Their image would get redder as the light from them gets stretched to longer wavelengths. They'd appear to freeze, suspended just above the event horizon, fading from view as the light redshifts into invisibility. From their perspective, they cross the event horizon in finite time. Nothing special happens at that moment. No wall, no sensation. They just pass through. But they can never send you a signal about what they experience beyond that point. Now let's talk about what happens to you if you keep going. You're falling in feet first because why not? There's something called tidal forces. Gravity gets weaker with distance. The difference in gravitational pull between your feet and your head, normally negligible, becomes significant near a black hole. Very significant. Your feet are closer to the black hole than your head. They experience stronger gravity. They're being pulled harder. The difference in force starts to stretch you. We call this spaghettification. I'm not making that up. That's the actual term. For a stellar mass black hole, this starts happening well before you reach the event horizon, tens or hundreds of kilometers out, depending on the black hole's mass. The tidal force grows stronger as you fall. First, it's uncomfortable, then painful. Then your body starts to deform, stretched lengthwise, compressed from the sides. You're being turned into a human noodle, pulled thinner and thinner. Your bones break. Your cells rupture. You're pulled apart at the molecular level, then the atomic level. You become a stream of atoms falling inward, a thread of matter, maybe a few atoms wide and thousands of kilometers long. This happens before you even cross the event horizon. Now here's the thing. For a supermassive black hole, this process is much gentler, at least initially. The tidal forces at the event horizon are far weaker because of the black hole's immense size. You could, in theory, cross the event horizon of a supermassive black hole and still be intact, still alive even. Not that it would help you. You've crossed. You're inside now. This is what no one can ever report back about. Every path you can take leads to the singularity. Time and space have swapped roles. Just as you inevitably moved forward in time outside, you now inevitably move toward the singularity. It's not in front of you in space, it's in your future. You can no more avoid hitting the singularity than you could avoid tomorrow arriving. How long do you have? It depends on the black hole's mass. For a stellar mass black hole, from event horizon to singularity is a matter of microseconds. For a supermassive black hole, it might be hours. Long enough to think about your situation. Long enough to really contemplate what's happening to you. The tidal forces keep growing. Even if they were gentle at the event horizon, they become infinite at the singularity. You're still being stretched. Still being compressed. The process that might have killed you outside continues inside, but now there's literally no escape. What do you see? The universe outside would appear to age. In principle, you could see the entire future history of the universe play out in compressed time above you, blue-shifted and accelerated. Though whether you'd actually observe this before tidal forces destroyed your eyes is another question. And then, the singularity. We can't describe what happens there. The math breaks. Physics as we understand it ends. But you're gone. Converted into something we can't explain with current theories. Your information might be preserved somehow. There's a famous debate about this, the black hole information paradox. But in any practical sense, you're destroyed beyond any concept of destruction you could imagine. Here's something that surprised everyone when Stephen Hawking figured it out in 1974. Black holes aren't entirely black. They emit radiation. This is quantum mechanics meeting general relativity in a weird and wonderful way. In the vacuum of space, particle-antiparticle pairs are constantly popping into existence and annihilating each other. This happens everywhere, all the time. Usually you don't notice, but right at the event horizon, something interesting can happen. A particle-antiparticle pair appears. One falls into the black hole. The other escapes. To an outside observer, it looks like the black hole just emitted a particle. This is Hawking radiation, and it has a bizarre consequence. Black holes evaporate. They lose mass over time. Incredibly slowly, but they do. For a stellar mass black hole, the temperature of this radiation is measured in billionths of a degree above absolute zero. The time it would take to evaporate is around 10 to the 67 years. That's a 1 followed by 67 zeros. The current age of the universe is only about 1.4 x 10 years. But smaller black holes evaporate faster. Much faster. A black hole with the mass of a mountain would evaporate in about the age of the universe. A black hole the mass of a car would explode in a burst of gamma rays in a fraction of a second. Here's the thing, though. As a black hole loses mass, it gets hotter. The radiation increases. The evaporation accelerates. In the final moments, a black hole would release an enormous amount of energy in a final explosive flash. We've never observed this. We've never detected a primordial black hole from the early universe exploding. But the math says it should happen. In the far, far future, long after the last stars have died, long after the universe has gone dark and cold, black holes might be the last sources of energy, and eventually even they'll be gone. So where are all these black holes? How many are there? In our galaxy alone, there are probably 100 million stellar mass black holes. Maybe more. Most of them are completely dark, invisible, detectable only if they happen to have a companion star they're pulling material from. The closest known black hole to Earth is about 1,600 light-years away. That's close on cosmic scales. Incredibly far by human standards. There are likely closer ones we simply haven't detected yet. And then there's Sagittarius A*, the supermassive black hole at the center of our galaxy, 26,000 light-years away. We've observed stars orbiting it at thousands of kilometers per second. One star, S2, has an orbital period of just 16 years and gets as close as 17 light hours from the event horizon. That's close enough that relativistic effects are measurable. We've used these observations to test Einstein's general relativity in extreme conditions. So far, Einstein's still right. Nearly every large galaxy we've observed has a supermassive black hole at its center. The mass of these black holes correlates with the mass of the galaxy's central bulge. Somehow, black holes and galaxies grow together. They influence each other's evolution. The jets of material ejected from active supermassive black holes can regulate star formation across the entire galaxy. Black holes aren't just cosmic curiosities. They're architects of the universe's large-scale structure. Here's what's going to happen. Our sun will never become a black hole. It doesn't have enough mass. In about 5 billion years, it'll become a red giant, swell up and possibly engulf Earth, then shed its outer layers and leave behind a white dwarf. But larger stars out there are dying right now, creating new black holes. The universe is making more of them all the time, and black holes are merging. When two black holes spiral into each other, they release gravitational waves, ripples in space-time itself. We've been detecting these since 2015 with LIGO and Virgo. Each detection is a glimpse into one of the most violent events in the universe, the merger of two black holes, combining their masses, releasing more energy in a fraction of a second than all the stars in the observable universe emit during that same time. But it's released as gravitational waves, not light. Space itself rings like a bell. In the far future, after all the stars have burned out and the universe has expanded into cold darkness, black holes will be among the last objects remaining. They'll slowly evaporate through Hawking radiation over timescales that make billions of years look like nothing. 10 or 67 years. 10, 100 years. Numbers so large they're almost meaningless. And then eventually even the black holes will be gone. The universe will be a thin, cold soup of fundamental particles, spread across an ever-expanding space, approaching absolute zero. That's the heat death of the universe. Probably. If our current understanding is correct. Black holes are terrifying. Objects that break the universe. Places where our best theories admit they don't have answers. Regions where you could cross an invisible line and be forever cut off from everyone and everything you've ever known, falling toward a future you can't avoid and can't survive. But they're also natural. They're what happens when gravity wins. They're the inevitable consequence of physics playing out according to the rules we've discovered. And far from being rare aberrations, they're common. Fundamental to how galaxies form and evolve. Essential pieces of cosmic architecture. We've come remarkably far in understanding them. 100 years ago, we barely knew they could exist theoretically. 50 years ago, we weren't sure they were real. Now we've photographed them, detected their mergers, tracked stars orbiting them, tested our deepest theories of reality against their extreme conditions. But there's so much we still don't know. What happens at the singularity? How information is preserved? How the first supermassive black holes formed? Whether there are undiscovered types of black holes we haven't even imagined yet. Black holes are a reminder that the universe is stranger than we think. That there are phenomena out there that challenge our intuitions about reality. That the cosmos doesn't care what makes sense to human minds evolved on a small planet orbiting an ordinary star. And yet we keep figuring it out, bit by bit. Observation by observation. We're clever apes who looked up at the sky and decided to understand everything we could see, and then kept going to understand what we couldn't see. Black holes won't hurt us. The ones that exist are far away, and they're not coming to get us. They're just out there, being what they are. The universe at its most extreme. And we're here, trying to understand them. That's pretty remarkable when you think about it.